Amplitude Spectrum Analyzer can help to understand your data before performing AVO attribute analysis or inversion. This is our AVO workshop Gulf of Mexico dataset. The play is the sand reservoir up deep capped by the interpolated horizon. Before performing detailed AVO analysis and inversion, a gather preconditioning workflow is applied. The workflow basically involves a few processes. Starting from the wheel on the left, an ultimute and long offset residual NMO has been applied. At the middle panel, a spatial balancing is done to increase the resolution and event definition. Trim static is used to flatten the events more. Last, on the right, a supergather with a 3x3 rolling window is used to smooth the data laterally. Some processes will affect the frequency contents of the data. This Amplitude Spectrum Analyzer can help to quickly QC the processes. Let's see how much correction has been made to the data. The Amplitude Spectrum Analysis tool is put under the Processes, Seismics, Utilities, and Amplitude Spectrum Analysis. We double-click to start. Once it is started, you see the setup area allows you to open the input seismic, or you can go to the project data list, seismic. We want to first look at the long offset RMNO output data. You drag and drop to the wheel. What you see here is the first line of the 3D data. Close the setup area to give you more space to look at. From the selector on the top here, you can pick up a location or a line which is cutting through a well. You select it and the location is highlighted here. What you see is the stacked version of the seismic. Input data is pre-stacked, but what we see here is post-stack. The stacking process is done on the fly, allow you to identify your location sooner and quicker. Within the main window of the analyzer, at the top part is the setup area. The setup area allows you to look at different panel or different way of looking at the seismic data. The checkbox here is called the time offset gather. So it shows you the actual original gathers at that particular locations. You can also turn on frequency offset gather, which show the frequency spectrum of the offset data at that particular CDP. As you expect in most of the offset data, so you will see a decrease in the amplitude range against offset. We want to compare the frequency contents of different seismic volumes. Let's restore down the first window, start another analysis, and then look at the spatial balance data. What you see here is the second data set that have done spatial balancings. To illustrate the spatial balance, we can look at the output of any particular CDP. Let's say go to the same one at the well location. If you compare the one without spatial balancing and the one with spatial balancing, you can see that the amplitude spectrums equalize, and from near offset to far offset, they have the same frequency range. At the lower bottom here, we have an option to turn on the amplitude spectrum sections. Then you will see the amplitude plot along the line chosen. In this dataset, the frequency range is less than 50 Hz. So what we can do is to limit the plot range to say 50s. Because we know that this dataset is looking at the sand layer, what we can do is to set a target window. Look at the event at M4 sand T with a range of say 400 milliseconds only, and then apply. We can do exactly the same windowing on the spatial balanced data, and then turn on the amplitude spectrum. Here we compare before and after. There's an option to normalize all the plot. Then we see the normalized spectrum. By just looking at the shape of the spectrum, you can see the flattening of the spectrum using the spatial balancing better. If you recall, we have 3 outputs from the gather conditioning process. Let's see how fast we can compare the output of the final super gather. If you go back to start a new Amplitude Spectrum Analysis sections, go and look for the final super gather, create a plot, and then set the target window to the SAN 400 milliseconds, looking at 50 Hz, and normalize the spectrum. You see the data of the final super gather, automatic CDP step version, and then the amplitude spectrum. We can compare the 3 seismic data sets and see how the frequency content has been changed. Let's look at the spectrum of the final super gather. One typical use of this plot is to determine the high-cut corners of the low-frequency model for inversion. On the bottom right here, you can set and change the display parameters. They allow you to change to different color scheme, for example. For analyzing amplitude, quite often we have to change the trace excursions. So we provide a slider, allow you to change it easily. Other than that, a toggle between color and wiggles can be done right here next to it. For spectrum, you can plot every flip trace, for example. From the button here, you can start the amplitude spectrum curve. To guide the selection of location, we can turn it back to the CDP step section, traveling up the using double click, single click, and the mouse cursor to identify the curve at different locations. Selecting location using the map is the most efficient way to do so. The Show Map button allows you to look at the survey grid as a start, but you can also turn on other project data. For example, drag and drop a horizon onto that map. Or if you have other information like seismic amplitude data slice, you can also select and drag and drop it onto the map for your reference to select locations. In order to select the best location for your analysis, you can click on the map at different location. Again, using the same style, a double click is to select a location which indicates that blue, and then move to a second location and then do a single click. Then you have 2 curves to compare. For the next version, we will avoid the stationary trace assumption. What we have here is called a spectral decomposition analysis. It's the same data, but we're running the continuous wavelet transform on the CDP trace, stack trace. If you look at the spectrum plot, you can analyze the frequency attenuation at different sample locations. And then you can look at the gradient change and or the notch frequency that you can detect from the seismic data.